Good evening. Let Adar join when still we have 15 minutes.
I just wanted to check my audio is visible. Sound is okay.
Sound is okay.
Okay, good. That's why I joined, just to check.
So even if you wish to check the slide sharing, means you can.
Yeah, I'll just do that. You have to enable it. It's still disabled. You have to still enable the sharing.
I think Professor Pathak, you are not audible.
Please try once again. Means this sharing option is.
Yeah, now it's there.
It is visible.
Yeah, it's like I'm not being able to get it on slideshow. Yeah, is it on slideshow also now?
Now it's full screen.
Yeah, okay. So that's.
And slide change is also happening.
Okay. Okay. I'll just minimize it. Or should I unshare?
Hello, Anirban. Hello, Enakshi. Can you hear me?
Yeah, good
Yes.
evening. Good evening, sir.
Good evening. Good evening. How are you?
Fine, thank you. Thank you for this opportunity to be on this forum today.
ये सब अनुराग का कमाल है. Anurag and Papia.
Anirban and Papia, I think,
Yes.
get the
Yes.
credit for this. Thank you. I somehow have not given talks on these forums, although at the university level and various colleges of University of Delhi I've spoken quite often, but forums like this somehow have not really been there for me.
Papia, is this the best time to choose 6 o'clock? I don't know. I thought
Papia, you are muted.
Oh,
Huh?
yeah. Till now,
So
now.
actually, initially we thought that this will not clash with the teaching duties, means at least nobody will have any class at that time.
but now in colleges, everyone has to go to a college, right?
Yes.
Yes.
So they will.
They return only at about, but most people return pretty early from at least Delhi University colleges. There's a major transition happening in the courses of University of Delhi.
Yes.
Is it happening in most of other organizations also?
Is it now going back to the 4-year program?
Yes, yes, with effect from this academic year.
4 years, the same thing that we got
That-
rid of.
What that Professor Dinesh Singh proposed ran for 1 year and then it closed down. And also I understand
What-
quite similar with foundation courses in the first year and decision making to which course to take in the second year. I don't know how they will achieve it because that's not the admission structure at Delhi University. I don't know what they will do. And also, sir, all undergraduate admissions will happen through the central test, QSET.
Yes, that I have said, but it is it is sort of going back to few years back there was this 4-year program.
Yeah.
And they
And
dismantled it.
Professor Mukunda was most important person in that.
Oh, I didn't know that. I didn't know that.
He was leading the panel who recommended this.
Recommended the 4-year program.
Yes, means.
That was 2013-12.
So there was a panel and Professor Mukunda was chairman of that panel.
But I don't know, it was implemented only in University of Delhi. Nobody else did it.
But was it successful in Delhi?
Sir,
No, but it was dropped next year.
It was dropped next year, so it wasn't really a program. I mean, it was just dropped in a year. And so people had to go back to doing the old syllabi in rapid mode.
No, as I understand, this 4-year was to happen because the country has signed an accord with Washington Accord, where you have to make this 4-year. So whether this government likes or that government likes, eventually it had to happen.
Professor Ajit Iqbal Singh, good evening, ma'am.
Good evening. I'm looking forward to your talk.
Oh, it's not very great, but I'm glad to see you, ma'am. How are you?
Yeah,
Nice to see you,
fine,
ma'am.
thank you. Fine, thank you. How are you?
Fine, thank you. I also
I
retired.
had met you briefly somewhere. I don't recall where.
Now recently in ISI meeting, we were attending all the talks together,
Yes.
of course in the distant mode.
Hello, ma'am.
Allahabad Nasi meeting. We travel together.
Yes.
And Enakshi brings back so many good memories.
That is true.
Campus,
That is true.
Nice.
Nasi is right now going through a crisis.
Yes, true.
Only Nasi or all academies?
I don't know about other academies, but Nasi is going through a crisis, and it has only a handful of people, 18 people. That is something.
So it's almost 6 and we'll start in 1 minute. We'll start on time, and then people who are late, they may join later.
Yeah, in any case, it's a generalized, sort of more or less general talk, so it's okay.
So it's 6, and as we planned, we'll start the program from 6. And so before this talk, the third talk in this series starts, we just want to tell a bit about the background of this program. So as you all are aware of the activities of NASI, and the NASI is more oriented toward implementing science for society. And NASI has a regular program on science and society. And on the eve of 75 years of independence, the government asked, among all other academies, NASI also to organize some programs bringing science to the society. And part of that initiative, Science and Society initiatives, all the chapters have been asked to do some specific programs on, and NASI Delhi chapter took several initiatives, and one of those initiatives is to organize a series of talks called NASI Women in Science Lecture Series. And the idea is to organize talks by eminent women scientists and to encourage young women scientists or would-be scientists, undergraduate students, PG students, PhD students, or the women scientists who are in their early career, to give a message that it requires some effort, but you can still do top-level science. So in the series, 2 talks have already been organized. The first talk was delivered by Dr. Manju Sharma, and the next one was delivered by Sohini Ghosh, and both were well taken. So we are now moving for the third talk of the series. But before we do that, it will be we need to formally introduce the speaker, and I ask my colleague, Professor Papia Choudhury, to introduce today's speaker.
Okay, thank you, Professor Pathak. So welcome you all on this third lecture of the Women in Science lecture series. And today we have with us Professor Enakshi Sharma. So let me introduce her first. And we are privileged that today we have such a prominent scientist with us. So Professor Enakshi Sharma is well known for her outstanding contribution in the area of photonics. She has recently retired from Delhi University, where she was a professor in the Department of Electronics Sciences. She joined DU in 1985 as a faculty, and prior to that, she did her MSc and PhD from Indian Institute of Technology, Delhi, in 1975 and 1979. She also worked with the Department of Physics, Indian Institute of Technology, New Delhi, as a senior scientific officer. At DU, she has worked as director, Center for Canadian Studies, and head Department of Electronic Sciences. She has also actively involved in many administrative activities in Delhi University. Her research interests are efficient analytical and computational techniques for design and analysis of wave propagation in optical fibers, integrated optical waveguides, and waveguide devices, analysis, modeling, and designing of doped optical fibers, which is EDF, and waveguides for the optical amplifiers. In these areas, she has published more than 100 research papers in many reputed international journals of higher impact factors. She was granted many research projects from UGC, DRDO, Ministry of Information Technology. She has also guided more than 20 research scholars. She was awarded National Merit Scholarship, Saraswati Gold Medal from Meerut University. She was also elected as visiting scientist under INSA DFG Exchange Program. She is an elected fellow of Optical Society of India. She is a member of IEEE, including MTT Society and Photonics Society. She is also a life member of ICTP Chapter of India. So we are privileged that today Meenakshi ma'am is with us and she will give an elaborative talk today for all of us. And so welcome ma'am. And I want to request you to give the talk.
I'll just share my screen.
Please share your screen.
Yeah, I'm doing that.
It's not at full screen.
Yeah, I know. You see that gets hidden there. I have to move. Yeah. Is it now full screen?
Now it's full screen and visible properly.
Yeah, okay. Well, before I begin, good evening, and thank you for giving me this opportunity to speak on this forum of Women in Science lecture series organized by the Delhi chapter of NASIM. I thank you, Papia, for a very kind introduction. And what I've decided to speak of is sort of my journey with light waves. I've spent almost about 45 years of my academic career looking at some form of light propagation. And that is what I plan to talk of in the next about 45 minutes to 50 minutes. My journey with light waves commenced with a very interesting NSTS, National Science Talent Summer School project under Professor Ghatak in 1975 at IIT Delhi, just after completing my MSc Physics. I couldn't go for the regular summer school due to some family circumstances. And this was a project on trying to understand mirage formation. So we all are familiar with mirage formation, or at least have heard of mirage formation in deserts, which essentially means that somebody sort of riding down a hot sandy surface in a desert sees not only the object, but also an image of the object under the ground, which gives an illusion of presence of water at that position. What we try to understand is this image formation by tracing rays through this graded index medium, because the air near the sand, hot surface, had a much lower refractive index than the air in the cooler part of above the surface, resulting in simple refraction, which actually follows Snell's law. So what my first exercise in light wave optics beyond the textbook was to look at this little problem. We considered a refractive index profile in which the index gradually increased rapidly from the surface of the sand to a distance away from it, used Snell's law in its differential form, which formed the ray equation. And with this, one could obtain a sort of analytical solution of ray paths in the stratified media. Also, my first experience in solving differential equations beyond the textbook and tracing rays. And I remind myself also often that it was days when we did not have a scientific calculator and one had log tables to trace all these cosine and exponential functions on a little red checkered graph paper. I did that, and it was a very nice experience to actually understand that, yes, there were rays which were, if an eye was at position A, there were rays which were reaching the eye straight to form the image of a certain point. And then there were rays which were refracted and turned around and also reached the eye at the position A, giving an image at the point where these rays intersected. It was very interesting to realize that an image is formed underground at a distance relatively closer than the actual object, and also another one there due to two rays in two different planes. And although we've always heard of mirage formations in deserts, you do realize that on a hot tarmac road in Delhi, you should be able to see a similar phenomena. And this is a picture from the web, not a picture we took. But I do remember driving down the road in front of IIT to check whether, yes, indeed, you see a mirage and the image formed underground is nearer to you compared to the project. It was a very interesting experience. And it also resulted in my first publication of my life in American Journal of Physics. Is this little thing at the bottom of the screen also visible? It's causing a lot of problem to me. Can I get rid of this cursor from here? I don't know. Okay.
We can see it clearly.
Oh, the full slide.
Yeah.
Okay.
We can see the entire slide.
We can see it properly.
Okay. So this was 1975, and 1970s was indeed an exciting time for optics in general. It was an era of emergence of optical communication and of new age, very innovative photonic devices. In fact, after the advent of radio wave communication in 1895, telecom engineers realized that higher the frequency of the carrier wave for electromagnetic wave carriers, higher would be the information carrying capacity. This led to an increase in carrier frequencies from kilohertz to short waves to high frequencies successfully. And finally, after World War II, one also reached 10 to the power of 9 hertz, which is the gigahertz range. At this point, maybe I should mention that Professor J.C. Bose in Calcutta had demonstrated communication using microwaves, in fact, more correctly, millimeter waves in 1895. But his motive was not communication, so he did not really get the credit for communication. But it was also because of lack of sources and detectors at these frequencies at that time. But by the end of the Second World War, gigahertz carrier waves were in use. Microwave communication had come in. If you look at light frequencies or light wavelengths, which are light is somehow more familiar to most of us in terms of its wavelength, which is in the 1 micrometer range, which corresponds to a frequency of about 10 to the power of 15 hertz, 1,000,000 times greater than the microwave frequencies. And hence it did seem to be, should have been the normal course for telecom engineers to look for communication for light waves as the carrier waves. But there were two reasons, I think, which deterred this. One, that light waves, for some reason, were always studied in a different domain and not as an electromagnetic wave, at least not for the engineering or the telecom engineers. And hence, although the basic nature of light waves as electromagnetic waves was established as early as 1865, they did not really fall into the regime of electromagnetic waves till much later. And also, strong, powerful sources in optics optical sources were not really available. It is the demonstration of the first optical laser by Meinman at the Hughes Research Laboratory on 16th May 1960, which gave this powerful source of light and hence immediately recreated an interest in optical communication, which, as I just mentioned, was 1,000,000 times higher in frequency and hence had that much more capacity than microwaves. This is a picture of Meinman's little apparatus, which is there at the archives of Hughes Research Laboratory. And this is a picture of the first setup in which he demonstrated lasing. However, unfortunately, we all know this, light waves do not travel through open air efficiently. There's a lot of scattering by air, dust, clouds, etc. Very familiar phenomena in metros like Delhi in the winters. And so one needed a channel for guiding light. This need for this channel resulted in the emergence of optical fibers as a channel for guided light wave communication. It's interesting to note that the concept of light guidance in optical fibers was based on a very simple principle of total internal reflection, which everybody studies in their school levels, that when light goes out from a optically denser medium to an optically rarer medium, it is refracted away from the normal. But once the angle exceeds what is known as the critical angle, that is defined by sine inverse of this, all the energy is reflected back. Based on this very simple principle, in 1956, a gentleman of Indian origin, Narendra Singh Kapani, invented what he called an optical fiber, where he used a core of glass of slightly higher refractive index and surrounded by glass with a slightly lower refractive index. This resulted in guidance through the structure by total internal reflection, at least that cone of rays, which made an angle greater than the critical angle at this interface, get totally internally reflected. All the energy stayed inside this little core, typically of diameters about 5 to 50 microns, and could go through long distances. However, Narendra Singh Kapani's objective was to create medical endoscopes, to look inside the stomach by passing the fiber light through the esophagus. And hence, typical lens he required were only 1 meter. And so even though the glass present at that time had losses of about 3000 dB per kilometer, this is a peculiar scale which may not be familiar to everybody, but what it implies is that if after 1 meter, the power lost is about half the input power. So if you had only 1 meter length, this was not so important. And so he was successful in using optical fibers for medical endoscopes. But after 1 kilometer, the power dropped to almost 10 to the power of minus 100 times P input. But in effect, there was no power left with these kind of losses. And so these glass fibers did not become a contender for use for light, as a light channel till much later, till after 1966, when Charles Cow and Hockham in Standard Telecom Labs decided to look at glass and the reason for losses in glass. And they realized that the glass, which was liberally available all over Europe had a very rich glass industry, had losses not because of glass itself, not because of what was the chemical composition of glass, silicon oxide, but essentially because of impurities. And so what he concluded was that the loss figure required by telecom engineers of about less than 20 dB per kilometer was much, much higher than the lower limit for losses imposed by glass SiO2 itself. In fact, he was awarded the Nobel Prize in Physics in 2009 for this work of 1966. So based on this observation and prediction, the Corning Glass Works, the 3 scientists whose names are there, Maurer, Keck, and Schulz at Corning Glass Works in the USA, fabricated glass. They did not use glass which was already available, but made glass, which was then extremely pure and could bring down losses to about 17 dB per kilometer in 1970. And within 2 years, the glass purity increased, so losses came down to about 2 dB per kilometer. This happened in 1970, so not too far back. In 1920, the world celebrated 50 years of the low loss optical fiber. And by 1977, the first fiber optic communication systems were operational. I should just mention that a very important accompanying breakthrough happened at the same time in 1970. although these ruby laser had been demonstrated, it was a bulky laser, and was not exactly compatible with dimensions of the hair-thin optical fiber. The breakthrough of semiconductor lasers from heterostructure devices with gallium arsenide, gallium aluminum arsenide, working for long periods of time at room temperature by Alfarov and Kromer, was a very important breakthrough for sources for optical fiber communication. They also received a Nobel Prize. This was in 2000. Incidentally, the Nobel Prize for them was not as much for the developing sources for fiber optic communication as much as for lasers to reach CDs. If you remember, the phase change lasers were being read by these little lasers. So why I told you this whole story is that everything happened somewhere in the 1970s, from 1970 to 1977. And I was fortunate to be at the right place at the right time to get an opportunity to join the fiber optics group at IIT Delhi for PhD under Professors A.K. Ghatak and I.C. Goel in 1975 to work on this emerging area of photonics, fiber optic communication and photonic devices. The picture you see is the convocation picture of my graduating batch in 1975. And at that time, I didn't see anything unusual in this picture, but a couple of, I think last year or so, a couple of years back, I just found this picture and scanned it to upload it on Facebook for my other classmates. And then I got a comment from Pratibha saying, I noticed that there's only one girl student in the batch. And then I had never thought of it, but when I stopped to think, yes, in the 1970s, even in IIT Delhi, even in a metro like IIT Delhi, girl students in STEM were still rare. And then I went back to think that the girls' hostel, only one girls' hostel at IIT Delhi had 40 rooms, while there were almost 5 boys' hostels. So 1970s, yes, women in STEM was still not in sufficient numbers. Although now we do not see that problem in university systems and in IITs, where IITs have, of course, have put in extra efforts to get in more girl students. But I should also mention that what was important is, even in my undergraduation, there were only 3 or 4 girls in my class in Dehradun when I was doing my BSc. But the important part was most of them went into professional lives. There was very little leakage down the pipeline for women who did venture into STEM education. A great motive for me going into STEM education was the award of the National Science Talent Scholarship after my class 11. And that was a big motive to take on STEM education and continue with it till PhD. By the time I joined PhD in 1975, optical communication had started taking over. In fact, some colleagues who had come in with me from under the QIP program of the ministry, I think to train teachers from other universities, there was always this question, will this little thin glass piece ever be used in communication? But that was to be. And the world had turned to digital communication by this time. So optical communication essentially meant these bits of information loaded on light wave, which in a broad sense, a common man's language would be narrow light pulses traveling through kilometers on optical fibers. So when we started working on characteristic of optical fibers, it was important to know what would happen to these pulses as they went through these optical fibers. Would they get broadened? If they got broadened, what would restrict the data rate? What would restrict the number of pulses you can send per unit time, etc. And by the 1980s, there was roughly a standardization that pulses would be of about 0.1 nanosecond to 25 picosecond repeat themselves at 10 to 40 gigabits per second through an optical fiber. Losses had, as I mentioned, were kept coming down and reached at a low figure of 0.2 dB per kilometer at the wavelength of 1550 nanometers, which corresponded to about 200 terahertz. So at 200 terahertz, 40 gigabits per second could easily be sent on one wavelength through an optical fiber. The losses were actually very low, 0.2 dB per kilometer. So about after 70 centimeters, still 4% power was available. And so people were not very worried. You could use a 70 kilometer repeaterless span and put a repeater after 70 kilometers. Then came in a more interesting phenomena. We all know that different wavelengths in a typical, for example, coming from the sun or the white light of the sun has a large number of wavelengths, and it's possible to separate them maybe with a prism, as we've seen in school experiments that you can separate. Similarly, one could send a large number of wavelengths, each carrying 40 gigabits per second through this little hair-thin optical fiber. So if you could send 100 wavelengths from 1520 nanometers to 1560 nanometers through this little optical fiber, the capacity would increase to more than terabits per second. That is what then happened to increase the capacity significantly. But remember, the losses were still there. So when people wanted to put a transatlantic transmission link from New York to London, for example, which is about 7,000 kilometers, it would imply a huge loss of 1400 dB. I mean, you couldn't send enough signal to go through the whole length without losing it. One needed to amplify it every 70 kilometers, putting conventional amplifiers for detecting each wavelength, amplifying it, and then sending it again required a lot of sources and detectors, which was quite a challenge for undersea communication. But fortunately, a great invention happened in 1985, the development of an erbium-doped optical fiber amplifier, which could amplify signals based on the same phenomena as a laser works, and could directly amplify the whole range of signals being sent under WDM, in the WDM channels, the whole range from 1520 to 1560 nanometers. And this transformed the total optical communication networks. This transformed the total communication networks. You had multiplexers by which all these wavelengths were sent down long stretch of optical fiber. After every 70 kilometers, this optical amplifier was pushed, and at the end, these were demultiplexed, getting terabits per second capacity for the link. So today, as we scroll through Facebook, Instagram, or queue up for an episode on Netflix, we rarely give a thought to that hidden network of fiber optic cables that instantaneously shuttles all this information around the globe. An extensive network of these cables, which could cover around the equator about 30 times, is what is the connecting tissue which binds the internet today. This is a picture showing all the undersea cables that run around the whole world. Another important thing happened simultaneously. Progress in guided light-walk communication in optical fibers triggered the growth of what came to be known as integrated optics, to build integrated optical circuits, very similar to microelectronic circuits. Microelectronic circuits are the integrated electronic circuits which today create all the chips that we talk about in electronics. The backbone of these integrated circuits were dielectric optical waveguides, basically lights which could confine, structures which could confine light to order a few wavelengths on planar substrates. And it was understanding light wave propagation in optical fibers and optical waveguides, which was my first endeavor from about 1975 to 79 and led to my PhD dissertation. After finishing PhD at IIT Delhi, I stayed on at the physics department of IIT Delhi and had an opportunity to work with a lot of young and older colleagues, which was a big learning process because your postdoctoral experience is always more fruitful, because by that time you've matured enough to learn how to learn new things. And after spending about 5-6 years at IIT Delhi, I noticed that a new department of electronic science had come up under the Faculty of Interdisciplinary and Applied Sciences at University of Delhi South Campus. And they advertised for positions for reader. And this was an interesting department. It ran a master's course in electronics. And since this course had been formulated in the 1980s, which was after the advent and development of optical communication, someone in the picture realized that optical communication and optical devices were going to become important. And so the coursework consisted of full theory and laboratory courses in optical electronics and quantum electronics. Another full-time course that was running there was microwave electronics. And of course, there was the possibility of PhD programs. I applied for a reader position in this department, and I realized at the time of interview, when the Vice Chancellor showed me a list of courses that had to be taught, that perhaps no one else who appeared in the interview said they could teach the theory and laboratory courses in optical and quantum electronics. Because I don't think till then very many institutions in India were doing courses in optical electronics and quantum electronics, except perhaps IIT Delhi. So the good fortune of being at the fiber optics group at IIT Delhi also led me to getting an appointment as reader in the Department of Electronic Science, where I spent the rest of my academic career and contributed to significant areas of photonics in its own different ways, long period gratings, microwave. The department ran a full program on microwave electronics, which means I had colleagues who had specialized in microwaves, and combining with them, I could work on this interdisciplinary area of microwave photonics. I'd worked a lot on optical waveguide devices, which was my fundamental training at IIT Delhi. And then towards the end of my career, a little bit on optical fibers and sensing. But importantly, I had a lot of role to play in development of the theory courses and laboratory courses in optical electronics and quantum electronics. And I had to date, about 600 or more students must have gone through these courses, which I taught them across all these years. I should mention that naturally my areas of contribution in photonics was with my PhD students. I mentored about 20 PhDs, a little more than 20 PhD students. But importantly, I would like to specially mention that 14 of them were young women. And each of them has grown well in their professional lives. I think part of their training or stay with me in my group was also how to balance professional life with domestic responsibilities. Maybe if you speak to them today, they will definitely say that, yes, it was a training that they got in those 5 to 6 years that they spent in my group at Delhi University. As I mentioned, this was my basic training at IIT Delhi, was on optical waveguides. And then we moved on to guided wave optical devices. And a lot of my students, right from 1985 to, in fact, today, 2022, have worked on a lot of devices based on couple waveguides. So what I'll do now is briefly go through these devices, which these sort of contributions that were made along with my PhD students. Just for those who are not so familiar with optical waveguides on planar structures. The optical fiber was a waveguide which guided light, but it was in a circular cylindrical configuration. A similar configuration on a planar substrate is what I call an optical waveguide. It also has glass. The first earliest ones were also glass. So there was glass, then there was a glass with a slightly higher refractive index created by doping it with some other little element, and then another layer of glass. So this also formed a low index, higher index, low index structure, and light could be guided through a similar phenomena like total internal reflection. But to understand optical waveguides, it was important to now understand electromagnetic wave propagation in these waveguides, just as most of us who did physics undergraduation or graduation used to look at metal waveguides used in microwaves and radio waves, which were essentially rectangular metal cross-section pipes. And what one used was solutions of Maxwell's equations or electromagnetic equations to obtain specific field patterns which propagated in these waveguides with specific phase velocities, or specific patterns. Similarly, in these waveguides, one can also solve the same Maxwell's equation and look at how the light is confined in different patterns in this region of this waveguide, and these are mode patterns are referred to as modes. I don't want to go into great mathematical details of it. The early waveguides, as I mentioned, were silica waveguides. Now, silicon on insulator. Insulator is SiO2. Insulator is a common terminology used in integrated electronics, CMOS circuits. Waveguides in silicon and silicon oxide again correspond to high index silicon, low index silica outside. And because the index of silica is very high, these waveguides are much smaller in dimension than the waveguides that you had in silica glass. These waveguides confined light only in one dimension. Sort of, you notice that if you put in a ray of light, it's only a one-dimensional confinement. In this direction, there was no confinement, and they were referred to as 1D confinement waveguides. But if you could put again a low index medium here and low index medium, they would give you two-dimensional confinement. So the early two-dimensional confinement was obtained by diffusing titanium into lithium to increase the refractive index of lithium substrates in a certain region and create a waveguide quite similar to what you would look at in optical fiber. And similarly, a silicon slab on silica glass created a two-dimensional waveguide in silicon photonics. Silicon on insulator has become the most popular backbone of photonic integrated circuits in what is today referred to as silicon photonics. The reason for that is silicon technology has significantly matured with CMOS fabrication in electronic circuits. The CMOS fabrication is of commonplace for electronic ICs. And so this is compatible with that and has become the most popular platform today for photonic integrated circuits. Just as I look at this is the field profile, or how the field propagates along the Z confined to a little region here. Similarly here, the field is confined to this region. But if you notice in these field profiles, there is a significant amount of field also in the tails beyond the waveguide dimensions. It is also visible here, and this is its decaying field, usually referred to as an evanescent field. And I'll skip this for the tip. And because of this evanescent field, if you bring two waveguides very close to each other, the fields tend to overlap. The field of this waveguide penetrates into this. This is also two waveguides very close to each other. And these configurations are usually referred to as evanescently coupled wave. And they form an extremely interesting configuration for a lot of waveguide devices. In fact, I got interested in this coupled waveguide configuration very early in my career in Delhi University, and we did a lot of work with my students on looking at these evanescently coupled waveguide structures. And we had a lot of publications in this. How do we handle these structures? So this itself is an independent waveguide. This is an independent waveguide. But when they come close together, they start interacting. And if you put in power in one waveguide, power tends to go in this waveguide and can also come back and so on. So this formed a very fascinating study for me in the early days. And one of the techniques used to study this was referred to as couple mode theory, in which you said, okay, I put in light here and let me try and see how it is distributed in the two waveguides and how does this distribution change. So this defines the distributor into both the waveguides, waveguide 1 and waveguide 2, and how this evolves with propagation decides what happens to the power in the two waveguides. This couple mode theory was an analytical tool, and that is why with my training in an analytical work, I was very happy to handle it, and my students also learned how to handle couple mode analysis. And it resulted in simple analytical solutions on how power, when launched in one waveguide, would move to the other waveguide and come back. And an interesting thing, what these little analytical equations showed was that if the two waveguides had the same phase velocity or propagation constant, as it is called, complete power transfer would happen, and otherwise it wouldn't. And a little later, a lot of simulation tools, although we did analytical work and did plots of these in line plots on graphs. A little later, we managed to get some commercial simulation tools. Essentially, I think it is Photon Design from UK. And my students could simulate this process of power transfer between the waveguides. So when the waveguides were identical, or at least had identical phase velocities in them, one got complete power transfer between the waveguides at, I don't know why it keeps changing, at a specific distances. And if they were different, the waveguides were different, it was a non-synchronous. Or non-synchronous, the power transfer was not complete. Okay. I did mention at some point that, in fact, to quote Feynman, the similarity between physical equations often allows physicists to gain understandings in fields beside their own area of expertise. And if you look at it a little carefully, quantum mechanics and guided wave optics actually have a lot of similarity. So although most of us did not go through regular courses in guided wave optics as part of our graduation or post-graduation programs, we all did a lot of quantum mechanics. And it was quite a nice experience to be able to sort of translate what we learned in quantum mechanics directly to use in guided wave optics. In fact, eigenmode analysis, variation analysis, perturbation theory, adiabatic evolution, I could at different points translate most of these things to use in guided wave devices. So exactly following the same story, you could look at these coupled waveguides by couple mode theory. One could also treat them as a multi-layer waveguide, find their modes and look at superposition of modes. And what we also did was use the variation analysis, which was familiar to everyone in quantum mechanics, to understand these two waveguides. So the refractive index profile of coupled waveguides is analogous to a double potential well. So following variational analysis, which is a textbook analysis in a large number of quantum mechanics books, one could also look at coupled waveguides, following exactly the same analysis. Two coupled waveguides, and then a student of mine did the same algebra on a waveguide array. So this was an interesting piece of application of what we learned in quantum mechanics to waveguide theory. The simplest device which came out of coupled waveguides was what was known as the directional coupler. If you put in power in one waveguide, you could get all the power or part of the power out from the second waveguide, depending upon the interaction lengths. And this became a very versatile device. I should mention that instead, it was conventional at that point to look at only two waveguide couplers. But a student of mine decided to look at what happened if there were three waveguides. Not exactly looking at any applications, because at that period of time, we did not really understand what photonic integrated circuits was heading to. But what she did conclude was to couple power from one waveguide to the third waveguide via the second waveguide. A little interesting condition had to be satisfied between the modes of this joint structure. And if and only if that happened, would you have it would be possible to transfer complete power. When we got the simulator, much later, when we got a simulator, this work was done almost in 1995, 2010, when we got a simulator, we checked this process, and yes, it did happen. We designed the second waveguide to be such that the condition demanded by the analysis was met, and we could show this complete transfer. But as I said, we did not have an idea, and we did not look at devices. But more recently, in fact, just last year, a PhD student of mine was looking for a device which would have, this is three waveguides, and he wanted to transfer. The three waveguides could have, the three silicon waveguides allowed two polarizations to pass through it. One which had its electric field normal to the substrate, and the other which had its electric field parallel to the substrate. The one normal to the substrate was the parallel to the substrate is usually referred to as the TE mode, and the one which had its electric field normal to the substrate was referred to the TM mode. And what he wanted to do was selectively couple the TM mode of this input waveguide one to the TM mode of the third waveguide, but not the TE mode. And he used this configuration which we had looked, similar configuration to which we had looked at 20 years back almost, to say that design these two waveguides, similar waveguides, and to change the dimensions of this waveguide so that that special condition of Na minus Nb equal to Nb minus Nc was satisfied, and he could simulate the performance of the structure as when the TM mode or the TM polarization was launched, there was a complete transfer of power to waveguide 3. But when the TE mode was launched in waveguide 1, there was no power transfer. So it became a polarization beam splitter. He used it in another photonic circuit recently. I would also like to mention that directional couplers have become an integral part of what is called the Mach-Zehnder configuration of photonic circuits. You have a 3 dB directional coupler, that is, which divides power equally. So if power is input here, it gets divided equally into this. These are the two arms of an interferometer. The power goes here and can come to another directional coupler. So when these two arms are identical, this 3 dB coupler acts to become a full coupler of full power transfer, and all the power would come out here. If there is a phase difference, there is a phase difference between these two, then you have power coming out in back here or here. In fact, this can form an electro-optic switch. So to form a switch, what you actually had to do was introduce a phase difference of pi between this path and this path of this interferometer. And why I told you this is, a student of mine recently designed this little such a Mach-Zehnder configuration in silicon nitride, and this phase shifting configuration using coupled waveguides, coupling between the silicon nitride waveguide and a waveguide formed by a material which is an optical phase change material. What is an optical phase change material? This is a material which can, by heating, be changed from a crystalline state to an amorphous state. And change from when it is in the crystalline state, it has an entirely different index than from when it's in amorphous state. And the amorphous state has very little losses compared to the crystalline state. So what the proposed design was that this material, when it is kept in its amorphous state, would be matched to the silicon nitride phase velocity, and there would be coupling from here to here and then back. While when it is the crystalline state, the two waveguides will not match and power will go through. And it's interesting to also note, which we also realized when we handled coupled mode theory, that when light travels from this waveguide, goes there and comes back in this total length, there's a phase difference between this and the one which would have gone through the string of pi. So what he did create is a phase shifter based on coupled mode, coupled waveguides. And this is a paper in Photonics Technology Letters. I did mention that a lot of quantum mechanics phenomena did get translated directly to optical guided wave optical phenomena. One of the phenomena which also found interesting application was Anderson localization. Anderson localization was predicted by Anderson in 1958 when he observed that disorder in crystals can completely halt transport of electrons, which actually implied that disorder in crystals would create a very high resistivity, while on a perfectly ordered crystal would have very low resistivity. The same thing, a student of mine tried to look at it analogously into or in fact, what it meant was exactly what we saw in GSST, that crystalline structure had a much higher loss, while amorphous structures had very little losses, because they did not, in an amorphous structure, there's no order, and then transport of electrons was not allowed, so it was not so lossy. My student Niharika looked at a waveguide array which kind of represented periodic potentials like a crystal did in quantum mechanics, and looked at power propagation. So this was a 21 waveguide array. When she put light in the central waveguide, when the waveguides were identical, white light spread across the whole network. But when there was some disorder, that means these were randomly disordered. The refractive index of each of them was changed a little randomly above and below n naught. She noticed that light did not now spread out. And when the disorder increased more, light remained here. So this was actually an optical illustration of what Anderson predicted in crystals for electron confinement in periodic potential wells. Some other devices which Niharika also proposed as design was a coupler between the silicon waveguide, which is usually the silicon waveguide is a very narrow, small waveguide of 220 nanometers by 400 nanometers. And optical fiber is about 4 micrometer to 8 micrometer. So coupling of light from a silicon waveguide to an optical fiber has been a challenge over time. Some techniques by using grating, etc., have been proposed. What Niharika proposed was again a coupled device. She proposed that one can couple light from the one mode of this waveguide, the mode of this waveguide, to one mode of this huge arrayed waveguide. And this huge arrayed waveguide had a very large field like this, while this waveguide, this little silicon waveguide, had a small field. By matching the phase velocities in these two waveguides, she could couple light to this and get almost 87% efficiency to the fiber. And another interesting thing which coupled waveguides shows is that if the distance between these two waveguides is reduced significantly, and one has a polarization which is polarized, the electric field is polarized along the substrate direction, which is referred to as the TE polarization, then because of this huge discontinuity here and the boundary condition that it is the displacement vector which is continuous, one can get a huge field in this little slot, which is also property of the coupled waveguide. And people like to use this structure in sensing because you have a huge field which can interact with an external material. But it has been a challenge to couple light from a conventional silicon waveguide to the slot waveguide, because the field here would be confined in this region, and to couple it to a field here was a challenge. One of my students recently did a design of such a coupling configuration in which the field from a strip waveguide adiabatically evolved to the field of this was an adiabatic evolution of field, exactly like you have the adiabatic condition in quantum mechanics in time dependent, when the Hamiltonian is time dependent. And so in that case, the mode profile changes as it propagates, but the mode power remains in the same mode as it started. So this is again an application of some of the quantum mechanic phenomena. And finally, a very interesting application. This is my last PhD student who should be submitting at the end of this year. Decided to look at optical interconnects. Now, what is an optical interconnect? Optical interconnects on electronic chips have suddenly started gaining importance because metallic microstrip interconnects, normal metallic strips interconnecting different parts on a chip, can become extremely lossy when operating at gigabits per second. At high frequencies, these metal strips become very lossy. When I say they become very lossy, it means that the resistive ohmic losses are very high, which then implies that a lot of heat is generated on the chip and the cooling process becomes extremely important. So to avoid that, people have started thinking of using optical interconnects, which means that the electrical signals are converted into optical signals and sent down a waveguide. These waveguides are these individual signals can then get multiplexed to a waveguide which carries large number of modes, and hence I call the phenomena mode division multiplexing. This huge trunk waveguide then carries the signal from one end to the other end, and where it is again demultiplexed to its individual channels. The core configurations of this multiplexing and demultiplexing are coupled waveguides. So what the proposed design was that you send in through a single moded waveguide, but this waveguide is phase matched or to one mode of this huge trunk waveguide. This trunk waveguide supports 3 different modal configurations. If this is phase matched to one configuration, this waveguide is phase matched to another configuration, and one field configuration is directly coupled. One gets actually a 3-mode multiplexing. And this is a picture which just shows what happened when power was sent in through this waveguide. It coupled to a mode like this, which had this field configuration. The one which came in through the center here had this field configuration, and the one which was sent in through the other one had a field configuration which corresponded to the TE2 mode, like this. And then at the other end, you have exactly the same reflected configuration, and they can be demultiplexed. Encouraged by his 3-mode multiplexer, in fact, when we sent it for publishing, the first comments was, if you tried for 3 modes, why don't you extend it to 5 modes? And so then he did do that. We had now finally a trunk waveguide which could support 5 different field configurations. And by these coupled waveguides, one could couple power to all of these 5 modes. All this was still one polarization, which meant the electric field propagating in these waveguides was always parallel to the substrate. Then to increase the capacity of these waveguides could support both polarizations which had the electric field parallel to the substrate and normal to the substrate. So Jyoti also decided to look at polarization division multiplexing. So we had mode division and polarization division multiplexers. And this is the configuration which he has now put together, which is now 7 channels put together to one trunk waveguide for an optical interconnect. This is still under the review process, and let's see what we have as comments. So this was a reasonably long journey with understanding couple modes in couple mode waveguide, and then applying it to devices. And I thoroughly enjoyed this journey with all my PhD students. And in fact, as I said, a large number of them were young women students, and they have been doing well. And this is the acknowledgements to all of them. This is the whole group of students with whom I worked. And I would especially like to mention Dr. Pragya Hijeb, who was not my PhD student, but came to me. I was her mentor in the DST Women Scientist Scheme recently. And Pragya came in after a reasonably large break in career, but coming to the group and staying with us and sort of learning how to balance work life with family life. She really learned a lot about semiconductor optical amplifiers. And in fact, I learned a lot about semiconductor optical amplifiers from her. Would also like to acknowledge all colleagues at South Campus and some colleges of Delhi University, each of them who contributed to my better understanding of photonics. And of course, a large number of collaborators from abroad. And of course, I should and would like to acknowledge my husband, Professor Anurag Sharma, who basically has grown in the world of optics with applied optics as his MTech degree, and then wrote a work on photonics. And our discussions at home on photonics have also contributed significantly to my whole journey in optics through the last 45 years. And this is a picture of the group of my large number of my students. We collected together at my retirement time. They gave me a very nice little farewell lunch. And it is with working with them that I really understood the basic concepts of photonic devices. And it was a great journey through my academic career. And I hope I would still be able to interact with young minds to learn more. Thank you.
So it was nice to listen about 45 years in 45 minutes. And now it's open for questions, comments, submissions. Anything means the participants want to discuss.
I wanted to unshare my screen. Yeah.
That was a great journey, Yanakshi. I'm very happy to hear the talk and your dedication to the field. For me, it has been an association of about 49 years with her.
49 years, yes.
49 years, and it was really a great pleasure listening to you, Meenakshi, and the variety of problems and the way you have contributed to the growth of so many young women and men, but particularly women. Today, I feel that that young women have to be nurtured and encouraged, which you have done in a tremendous way, particularly for young women who get married, maybe have children and things like that, to continue with work. You have shown that with your own example, how you have worked through and raising two wonderful children. So in today's world, at least in our country, we have to have much greater participation of women, much greater understanding on the part of the husband. And another great example is Papiya and Anirban. I'm so happy to see them grow independently and not grow, they are already very established scientists. That makes me feel very good. I want to tell Anirban something. You know, I have been wondering about, about the war in Ukraine. And I just thought that this president is already very old, how will he manage? So I looked up, I wanted to find out how old was he. And to my surprise, I found that he shares the same birthday as Meenakshi Sharma.
That doesn't speak very highly of it.
No. So I'm sorry for intruding, but those were all my. It was a great pleasure listening to you. Great pleasure. I would like to.
Sir, since you did mention that support
that
from home is very important, I should actually also acknowledge that I had complete support from my family, my own family, and Anurag across these years, with no significant demands either on my time or food or other things which is normally heard of from a lot of young ladies whom I've interacted with.
I can see any MSc students and our young PhD students. Means if you have any query or anything you want to share, speak.
See very many PhDs.
Unmute yourself and speak. I can see a couple of comments in the chat box also.
Okay, can I open the chat box? Yeah. No, I do have access.
So I can see comments from Professor Ajit Iqbal Singh, Dr. Bandana Luthra, Dr. Pratibha Jolly, Dr. Kiran Katach, and anyone, you just want to, because the chat is not probably visible to a speaker, so you can.
No, it is visible to me.
What you have written.
It is visible.
Okay.
In fact, it was Pratibha who pointed out to me when she saw the convocation picture that you are the only one who's a girl student in that 1975 batch. And that's when I realized, yes, I was. And I guess
the situation was not much changed with years, because I did my MSc in 96, 97, and then also
but she has to unmute herself. Pratibha, you have to unmute yourself.
Yes, it's...
Hello, Pratibha. It's nice to have you here.
Yes, and it's been such a lovely talk. And I want to actually say thank you for all that you do that goes beyond academics as well. We've gained so much also from administrative support to the university and colleges. And the students are such a wonderful cohort. They do you proud. I think, and Professor Ghatak sir, your group is fantastic, So we just have to go up the ladder as well.
Yes, Professor Ghatak was my mentor and a role model. That is the most important. And I think we really need role models to follow even today.
But I also liked what you said about your family and Professor Anurag Sharma. You know, for Gati, I've been saying we need to celebrate our men colleagues and engaged fathers and engaged colleagues. Otherwise, gender equity is meaningless. So we can't talk of gender equity if we only look at the females. We have to talk also of the allies who provide the support.
In fact, Pratibha, since you mentioned it, I can mention that during the course of life with a lot of young students, young women students who got married while they were doing their PhD, there have been occasions when I've actually requested their husbands to come and visit me and had a long chat with them to explain to them how important the work of their wives is also, and they have to learn to sacrifice some of their little comforts for that. I've actually asked them to visit me in the office and have a long chat with them often.
Yeah, way to go.
Absolutely. I mean, there is no doubt about it that all young men or older men, should realize their responsibility in allowing their wives to grow, and the way Anurag has supported you, it is incredible. So I think a lot, as you correctly mentioned, and this is for others to learn. This is for others to learn whether your wife is in physics or non-physics, but to encourage her to participate, to contribute in some area in which she is good. And I'm sure all women, no matter how educated or how skilled they are, they can contribute. And that is extremely important. That is extremely important for the growth of, for the welfare of the system. I am 100% sure of that. For all young men in this audience, you have to propagate this. And of course, our government DST Women Scientist Program are there, but it has to come up in a very much bigger way. And so I must tell, some of you will know, some of you will not know. Professor Anurag Sharma, who is an outstanding photonics expert, but he also did his PhD with me and Professor I.C. Goel, and the proximity in the group. So I have made a small contribution to what. Chalo, sorry. So that is a very nice event, Papia.
Yes, thank you. Thank you, Anirban and Papi again.
No, before we close, I would like to request whoever is convenient to open the camera so that we can take a snap for record.
Yes.
Oh. So just take a minute, please. This will help us in annual report and such thing. So thank you everyone for joining this and making the event successful. And the event will actually be successful if the message which you wanted to propagate is getting propagated. Means that young students continue doing science and encourage young teachers encourage others to do science. So then only the purpose of the meeting will be successful, and we hope that will happen. And soon we will announce the 4th lecture of this series. And goodbye till then.
Thank you.
Thanks again.
Thank you and bye-bye.
Bye.
Thank you so much. Yeah. Thank you very much.
everyone.
Thanks, Papia.
Thank you.